Hi class. In this lecture here, we want to continue talking about hypothesis testing for two means, but by doing something different. We want to talk about what's called using paired samples. And so if you remember in the previous lecture, okay, we talked about hypothesis testing for two means with two independent samples. So if you think back to that lecture, the first example we talked about was test scores for students who used computers regularly in their class and students who didn't use computers regularly in their class. So we had two different groups. Paired samples is a little bit different. So what do I mean by paired? So a paired sample t-test is used to compare the means of two samples when each observation in one sample can be paired with an observation in the other sample. Okay, so here's some examples. So a measurement is taken on a subject before and after some treatment, so like the test scores of a student's before and after using a test prep program. We might do an example of that. Or a measurement is taken under two different conditions, like a response time or recovery time. Of a patient is measured on two different drugs, okay? So like for this example here, there's one student, this first example here, one student, but two results on them, right? So one student, and then we have a score before, and we have a score after. And so that's how they're paired. Each of these values is paired to this one student. Here in this example, we have one patient, and we have measurements on, say, drug A, and then a measurement on drug B. Okay, that's what I mean by paired. So how we go about testing this, right? So even though we're going to have two different samples, a group, a sample of one student's, but two different values, one before and one after. How we're going to go about this is a little bit different than what we did previously. Okay. All right, so we'll start this by this example by, or we'll study this concept by setting up an example for it. And so here's the question: does tuning a car engine improve the gas mileage? So basically, you buy a car, you drive it for a while, and then maybe the engine starts to not degrade, but just not run optimally. So basically what this is saying is if I take my car into a mechanic and ask them to, tune it up, whatever that means, tighten, change the spark plugs maybe, or check everything over and tighten anything up that's loose, would that improve gas mileage? And so here's the thing. I would like to think it would. Okay, so we think it would. Okay, so going for a tune-up should improve gas mileage. So yes. Getting the tune-up should improve mileage. I'm just going to put MPGs for miles per gallon. Okay. So how would you go about doing this, right? Like, you can't just compare one set of cars that have had tune-ups versus another set of cars that have had one set of cars that have had a tune-up and one that hasn't, right? Because they're different cars. So here's what you do. You take a sample of cars. Just a single sample, say, of 30 cars, okay? Then you'd measure on those cars their initial miles per gallon, then what you would do is give them a tune-up. So then give those same cars and then you'd measure their new miles per gallon. What you would actually then look at is you would see for each individual car how much of an improvement was there. So then what you would do is you'd calculate the difference of before and after. And then you'd perform a hypothesis test on that difference to see if that difference is statistically significant. So here's an example. This is what we'll work with here. All right, so we have a sample of 10 automobiles, okay? So that's our sample size. So you can see this is the first car all the way down to the 10th car. We're run to determine their mileage in miles per gallon. Each car was given a tune-up and run then again to measure their miles per gallon a second time. So the results are shown below. So what I have here, this is going to be our first result. I have this a little bit backwards, but what's going on here is you're seeing this is the results after the tune-up. So like, let's just look at this first car. After the tune-up, they were getting 36 miles per gallon. So maybe I'll just say this is the after result, actually. And then what we're seeing was before. This is their before result. We measure their miles per gallon before they got the tune-up. So like, look here. The first car got a tune-up. They got an additional 2 miles per gallon. The second car, when they got the tune-up, they went from 34 to 35. They got an additional mile per gallon. And so on. You can see most cars, it looked like it was a positive result. There was one car here that was a negative result. And there was one car here that showed no difference, okay? And so just look, a quick glance tells us the sample mean mileage was higher after the tune-up, okay? But what we're gonna try to test to see is that difference, is just the difference, all right, statistically significant, okay? So these are called paired samples because each value before tune-up is paired with the values of the same car after tune-up. All right, so now we want to perform a hypothesis test to see if that difference, okay, that we got there is statistically significant. It's meaningful. All right, so these are the types of tests we're going to run. And here's some notation. We're going to have d bar be equal to the sample mean difference of the differences between the values in the matched pairs. So going back, d bar would be the average of this row here, okay, of all these differences. S sub d is the sample standard deviation of the differences. Okay, so we take the, plug this data into our calculator, maybe find out what the standard deviation is of the differences. And we use U sub d, and this is going to be equal to the population mean difference for the matched pairs. Okay, and so we're going to have 3 tests here, and here's how we're going to set them up. All right. First, you'll still define 2 parameters. Okay. U sub 1, okay, is equal to the population mean for the first set of conditions. And it can actually, you can have U1 be the before or after conditions. It actually doesn't matter. And U sub 2 will be the population mean for the second set of conditions. So like, for example, in our first problem here, U1 will be our after result. It'll be the population mean miles per gallon after a tune-up. And mu sub 2, right, will be the population mean miles per gallon before a tune-up. And so then what we'll do is we'll define mu sub d, the difference, is just equal to mu1 minus mu2. We'll subtract them, and that's how we get the difference right here. All right, so the 3 tests we'll run. We'll run a two-tailed test. So our two-tailed test will look like this. Your null is always a statement of quality. it'll say, you know, we'll set the difference equal to some initial condition we'll call mu sub 0. This could be, oftentimes you'll see in the first example, this will actually just be 0. So what we'll do is we'll set the difference, you know, we'll assume there is no difference. So if there is no difference on average, then mu sub d should be 0. And what we're looking to see here is that no. It's not equal to this number. It's different. Then we could have a left-tailed test. Mu sub d is equal to some value, oftentimes again 0. And the alternative here is that no way. That difference is less than that number. And then we could have the right-tailed test. Mu sub d is equal to some number, and mu sub 1, the alternative, is that no way mu sub d is greater than that number. All right, and so just note often, mu sub 0 will just be equal to 0. We'll just, you know, assume that there is no difference to start. Okay, this means there is no difference. Right, so like if you want to, you know, test to see if there is a difference, you'll start with the assumption that there is no difference. So then again, you're just going to go through the five steps here of hypothesis testing. Okay, so it's going to be the same 5 steps. All right, the first thing you're going to do is define the parameters. I'm going to put an S here. All right. So define mu sub 1, mu sub 2, and then the difference, okay, which is mu sub 1 minus mu sub 2. And then you're going to set up a test. So you're going to pick one of the tests from the previous slide. Okay, so you're going to pick, is it a two-tailed, right-tailed, left-tailed, something like that. Then you're going to select the level of significance. For our problems, this will be given. And often it will be alpha is equal to 0.05. All right, then you're going to compute the test statistic, okay? And what this test statistic looks like, okay? T sub 0, it's equal to d bar, which is the average difference, minus mu sub 0, whatever you believe the difference, you know, your starting assumption of the difference would be often a 0, divided by s, divided by the square root of n. This is basically the same statistic from a one sample t-test. And so even though we have two kind of samples here, we have a before and after condition, we're actually just going to run a one sample t-test. So in our calculator, all right, going back to our calculator here, when we go to run this test, it's actually just going to be t-test here. We're not going to, in the previous lecture, we used option number 4, but here we're just going to actually use a t-test. So in calculator, use stat tests, and then here it was option number 2 for t-test. So here we're going to actually just let our calculator do this for us, and then we're going to compute the p-value, and again we will use the TI calculator for this. And then we're just going to make a conclusion. And you know what you notice with all these hypothesis tests? We boiled it down to one number, and then we boiled it down to one probability, the p-value, and you're just comparing your p-value to your level of significance. So your conclusion here is you reject the null, if the p-value is less than the level of significance, and you fail to reject the null, if the p-value is greater than the level of significance. All right, so I've got 3 examples here for us to work through to maybe, hopefully kind of understand and see this process. So let's first go back and let's figure out if, the tuning, all right, improves miles per gallon. Let's figure it out. All right, so a sample of 10 automobiles were run to determine their mileage in miles per gallon. Each car was given a tune-up and then run again to measure the measured miles per gallon a second time. So the results are shown below. All right. So at the 0.05 level of significance, is there evidence to suggest that getting a tune-up improves a car's miles per gallon? So the way we are going to define this is we're going to consider mu1 the mean miles per gallon after tune-up. And we're going to consider this, mu2, the mean miles per gallon before tune-up. And then there's their difference is mu1 minus mu2. All right? So let's test this. Okay? So again, let's go through the five steps in the hypothesis test. All right, in this case, let's define the parameters. I'm going to rewrite them again. All right. Mu1 is going to be equal to the mean miles per gallon a car gets after a tune-up. This reminds me, I should take my car in to get a tune-up. Mu sub 2 is equal to the mean miles per gallon of a car before tune-up. And then the difference is just mu1 minus mu2. All right, so now here's the thing. Now we need to decide how we're going to set up this test. And look, here's the claim, or what we believe, that after getting a tune-up, you should see an increase in your miles per gallon. So we're going to start with the assumption that there is no benefit by getting a tune-up. So the way we're actually going to set up this test is like this. Our null would be that mu sub d, the difference. We'll start with the assumption that getting a tune-up should not, change your miles per gallon, so that the difference between the two means, on average, should be 0. And then what we're looking to see is like, no way, it should be greater than 0. This greater than 0 implies that, hey, look, there's a positive impact of getting a tune-up. So level of significance, alpha is equal to, terrible alpha there. Let me resketch that. Alpha is equal to 0.05. Okay, and so now what we're going to do for steps 3 and 4 is we're going to plug in the difference into L1 in our calculator and use just the t-test, option number 2 in our calculator, the t-test. All right, so grab your calculators, all right? What we're going to do is we're going to go back. We're going to press stat, and under edit number 1, we're going to edit the list. And so what we're going to do is we're going to have to plug in all these differences into L1. So the first car got extra 2 miles per gallon. got an extra 1, 2, 2, 2, 1, 1, 0. Then this one car got a tune-up, a bad mechanic, and they got worse miles per gallon. And then this other one got an extra 3 miles per gallon. And so watch, to get the test statistic and the p-value, you're just going to go stat, test, option number 2. And what we have here is we have the data plugged in, right? We have the differences plugged in, so we're going to go under data. Our null is that the difference is equal to 0. Our data was in list 1. And we're going to scroll over to greater than because we're going to match the alternative. And when you do calculate, this is what you get. And look, here's what we're saying. Our test statistic right here is 2.7136. So basically, you're almost 3 standard errors away from 0. Like, that's a lot. And so the p-value here is 0.0119. 0.0119. So what does that mean? Well, look, the p-value is less than the level of significance. So you're going to reject the null. Right? This is because the p-value is less than the level of significance. And what this means is evidence suggests that on average, it won't happen for every car, as we saw, one car got a tune-up and got worse miles per gallon. So that on average, getting a tune-up improves miles per gallon. Okay. So basically the whole process here was when you have paired samples, you just calculate their difference, and then you run a one sample t-test on that difference. All right, let's do another one. All right. Let's talk about something called a crossover trial. Okay. So a crossover trial is a type of experiment used to compare two drugs. Okay, subject takes one drug for a period of time, then switch to another drug. That's the crossover. And the responses of the subjects are compared using matched pairs method, right? Because we have the same patient, but taking two different drugs. All right, so in an experiment to compare two pain relievers, okay, 7 subjects took one pain reliever for 2 weeks, then switched the other, okay? So then after another 2 weeks, basically they took a different pain reliever. And they rated their pain level from 1 to 10, okay, with larger numbers representing higher levels of pains, okay? And so the results are below. So basically this is what you're seeing. Under drug A, subject 1 says they had a pain level of 6. Under drug B, they had a pain level of 5. So patient number 2 under drug A had a you can see here, had a pain level of 3, and then it fell to a 1. But then, it's not always the case, right? Like patient 6 had a pain level of 1 and then a pain level of 2, okay? Can you conclude that the mean pain level is less with drug B, okay? So basically what they're trying to test to see here is like, all right, we had, drug A, all right, provided this much pain relief, and then drug B, okay, we're hoping they experience less pain, so it's providing better pain relief, okay? And so it's saying use the 0.05 level of significance. Now you'll notice here the difference is not given. Now you can very easily calculate it, right? Like the difference here would be 1, 2, -1, 0, 2, if you do A minus B and so on, okay? But I'm going to show you how to have your calculator actually do it very easily, okay? All right, so we're going to have drug A be represented by mu sub 1 and drug B represented by mu sub 2, So here's how we're going to set this up. We're going to let mu sub 1 equal the mean pain level taking drug A, whatever drug A is. And then mu 2 the mean pain level taking drug B. And then the difference, the average difference, is going to be mu sub 1 minus mu sub 2. All right, so now here's the hard part, right? You have to select the right test here. So what you want to see is that the pain level is less with drug B. Okay, so if it's less with drug B, what that means is the average of A should be greater than the average for B. Okay, because you want B to be less, right? That's what you're seeing here. You have the less sign here. So what we'll start with then, if you want to see if they're less, what you'll actually start with is the assumption that there is no difference, so that on average the difference is 0. And if you want B to be, the pain level to be less, then the difference should actually be greater than 0, right? Because this is what you should see here. Like when you subtract the average for B over, you see you're testing to see that it's greater than 0. Okay. So this is actually a right-tailed test. Level of significance was 0.05. Now your calculator will actually do something really, really cool. So grab your calculator and let's input the data, and I'm going to actually have the calculator calculate the difference. This is a really cool little feature. Okay. So watch, go into stat and edit under your list here. Go clear out list 1. And what you're going to do is you're going to put the pain levels for drug A in list 1. And then in list 2, you're going to put the pain levels using drug B. I think I said drug 1. I meant drug A. Now check this out. When you scroll over here, scroll up to the top where it says L3, and then you're going to have it, so you notice how it says L3 is equal to. In blue on my calculator here, you can see, let me try to make it bigger. You can see like L1 and L2. So I'm going to go L3 is equal to L1 minus L2 and hit enter. And look, right there is the difference. 6 minus 5 is 1. 3. See what happened there? 1 minus 2 is -1. It calculated the differences for us. So I'm going to go into stat, tests, t-test. And now here's what's crazy. Data, I'm going to check to see that the difference is 0. I'm going to assume, that the difference is 0. And then when I get to list, I'm just going to change it to L3 by going second function L3 here. Want to see if it's greater than 0 and calculate. And you should see something like this. It's saying here your test statistic is 1.3693. And the p-value here is 0.10. When I round it, it'll be 0.1100 basically. So then look, the p-value is greater than the level of significance. So we're going to fail to reject the null. So this is because the p-value is greater than the level of significance. And what that means is, on average, it looks like there is no difference in the mean pain levels of this drug. So even though we wanted to see if the drug B was better at reducing pain, on average, it actually wasn't. So no evidence to suggest the mean pain levels are difference between the drugs. All right, let's do one last one. All right, let's talk about maybe a student taking a prep class for an exam. Suppose a test company claims that their SAT math prep course will improve test scores by 10 points on average. Okay, so they're saying, hey, look, you take our class, and your SAT math score is going to go up by 10 points. Okay. To prove their course works, they sampled 32 students who took their course and recorded their SAT math scores before and after the class. Okay. Note here that the difference is 12.9375 and the standard deviation for difference is 13.5716. So the question here is, can you conclude that the mean increased score for those that take the prep course is greater than 10 points on average? Okay. So what they're saying is, look, take this and you're going to score more than 10 points. All right, boom. So you look here, you can see that the difference is indeed, here's actually the results for the students, their before and after scores. You can see that on average, this is greater than 10. But basically, is this really enough evidence to say that on average they're getting more than 10 points? Okay. All right, so basically, let me kind of change the claim. It will improve students' test scores by more than 10 points. All right, so we're going to test to see if indeed that's what happens. It is greater than 10 points on average. All right, so we're going to have the before and the after. Okay, and so look, because this difference is positive, what we're going to assume is mu1 is going to be the after and mu2 will be the before. So what's really cool is you can plug in the data like I did before and have it calculate the difference, but there's 32 students, you'd have to plug in 64 values, right? 32 for L1 and 32 in L2. But when I give you the summary statistics, you can actually just do t-test with the stats here. Let me show you. All right, so when you define the parameters, right? So we're going to let mu1 be equal to the mean SAT math score, excuse me. After the course, and mu2 is going to be equal to the mean SAT math, I put match, SAT math score before the course. So mu sub d is going to be mu1 minus mu2. And what the test actually wanted you to see is on average, our students scoring greater than 10. All right, the mean difference after you take the course is greater than 10. All right, that's what it's saying, we're greater than a 10-point difference. So then what our null assumption will be that, remember, when you set up these hypotheses, this has to be the same number. So we'll give them the 10-point difference, and then we're testing to see if it's greater than 10 points. Alpha is equal to 0.05. And now, let me go back here. what's really great here, and this is how quickly you can do this test. I have the summary statistics for the difference already. So when I go over to tests, I know I'm going to do a t-test here. I'm just going to click on stats. So here I'm going to start with the assumption that there's a 10-point difference. X bar, or the D bar, the average difference, was 12.9375. And the standard deviation was 13.5716. And my sample size was 32. Again, this I set up to be a greater than, right-tailed test. Unfortunately, all three of these were right-tailed tests today. And then hit calculate, and you should see something like this. Our test statistic is 1.2244 when I round it. The p-value here is 0.1150. And so look, p-value is greater than level of significance. You're going to reject the null. All right, here the p-value is greater than the level of significance. And so on average, we're not saying you actually score greater than 10. We can't say that it's, if it is 10, that's fine, but we can't say on average it's greater than 10 after taking the course. So no evidence to suggest that on average the students score more than 10 points. So more than 10 points on the SAT after taking the course, on the SAT math, after taking the course. All right, class, I know it was a lot to digest. As always, I'm here if you have any questions.